So the question is, where does this atmospheric pressure come from? Or where does this pressure come from when I go swimming and I feel that squeezing as I swim down to the bottom of the pool? And everybody's felt that. So I'd like to pretend this. The atmospheric pressure here comes from a column of air standing on my shoulders. So as I walk around this room, all the air above me is actually resting on top of my shoulders, and as I walk around, I'm actually carrying this column of air around me. Now, if I was in a swimming pool, I would actually be walking around on the bottom of the pool, and all the water that is above me would actually be resting on my shoulders, creating this weight, this pressure that I feel as I walk around in the bottom of the pool. Now, why is the atmospheric pressure so much less than, say, the pressure I feel in the bottom of a pool? Well, obviously speaking, water is much more dense than air, so as I go down to the bottom of the pool, it just gets heavier that much faster, and I start to feel that weight pushing down on my shoulders. So let me draw the picture of this column of water resting on my shoulders. So if we look here, here's this column, and here's good old me, and resting on my shoulders, I've got to hold up this entire column of, say, water on my shoulders. And it weighs quite a bit. So if I look here, there's a force pushing down on me. This force is the weight of the water itself pushing down on top of me. That's where the pressure comes from. So if we look there, our first thought is this. The force that's pushing down on me is the weight. The weight of what? It's the weight of the water. It's not my weight. What's causing that force pushing down on me is the weight of the water itself above me. And it's true. All right, now our second thought is this. All right, we know that density is equal to the mass divided by the volume. And if I rearrange this formula, we know that the mass is equal to the density times the volume. Same idea here. Now I can combine these ideas. Can I replace the m up here with the density times the volume? So that force of that water pushing down on me is going to be equal to, I'm replacing the m with rho times the volume. So I have rho times the volume times g. So the force of the water on me is rho vg. So that's a very popular formula. Now we also know that the volume of something is the length times the width times the height. So if we look at this particular volume, we know that the volume of any shape is going to be the length, width times the height. Another way of looking at that is this. Could I take the area of the top of the box and then take the area and multiply it by the height of the box? So volume is also known as not just the length times the width times the height, but the area times the height, and it's true. All right, so let's replace the volume in step number 4. So we have the force. Instead of writing the V here, I'm going to write rho A times H times G. So we have the force is equal to the density times the area times the height times G itself. Okay? And height is actually the depth of the water, isn't it? So as we look through there, that's true. Okay, now we also know that pressure is equal to the force divided by the area. So what I'll do is replace the F with rho AH divided by G. That's the force. And then remember, we can't forget about there is an area in the bottom. And we look, we have area in the top and the bottom. We can eliminate this like so. And voila, we discover that the pressure from the water pushing down at me at any particular depth is equal to rho H times G. So H being the depth of the water, it's actually how deep the water it is. So this is an important formula to us as we calculate the pressure that we feel at any particular depth.